Hi y'all, my multivar final is coming up pretty soon, so I decided it would probably be a good idea to do some review sheet or some sort of review video. So today I'm going over 3 theorems. We will be covering Green's theorem. There are 2 forms of it and we will cover both of them. Then Stokes' theorem, and finally divergence theorem. In case some of y'all might have already forgotten how to do line integrals and surface integrals, I will also briefly touch on those. Now let's get started. So first we have Green's theorem. We're mainly concerned in this case with R2, in other words, only in the xy plane. We're not talking about the z-axis just yet. We're going to expand the similar idea into R3 for the other 2 theorems, and I will explain it when we get to those 2 theorems. So for Green's theorem in the curl form, we have a vector field f. And Green's theorem is basically saying, if we want to calculate the line integral on the left, we can instead calculate this double integral over the region bounded by the curve. In fact, we also call the left-hand side of this equality the circulation of f. So to interpret the meaning of this equation, the left-hand side gives us the circulation, and the right-hand side says, to calculate the circulation, we can instead take this quantity qx minus py and integrate this quantity over the region bounded by this curve. In fact, we call this quantity the curl of f. When the curl of f is 0, we say the f is irrotational. That is, the vector field is not rotating along this curve. When the curl of f is larger than 0, we say that f tends to circulate in the direction of c, and when the curl of f is smaller than 0, we say that f tends to circulate in the opposite direction of c. Next, we have the flux form of Green's theorem, which is pretty similar to the one we talked about in the previous slide. Now we have f dot n on the left-hand side, which means that we're not concerned with circulation along the curve anymore. We're going across the curve this time. Same setup, but this time Green's theorem says, to calculate the flux, which is the left-hand side of the equation, we can instead take the quantity px plus qy and integrate this quantity over the region bounded by this curve. Very similar, right? But note that the integrand here is different. And we call this integrand the divergence of f. When the divergence is 0, we say f is source-free, meaning that there's nothing radiating out of the curve. When the divergence is larger than 0, we say f tends to radiate outward, and when divergence is smaller than 0, we say f tends to point inward. You might ask at this point, is it possible to extend this definition to R3? The answer is yes. But before moving on, it will really be helpful to introduce the del operator, which is written as partial x, partial y, partial z. Whenever we apply this operator, we apply these partials accordingly. For example, we define curl f to be the cross product between del and f. To illustrate how this works, let's look at the first term. So we first apply partial y to r, and then we apply partial z to q. We then subtract them to get our first term, and we do the same with the rest of the terms. Similarly, we can define the divergence of f to be the dot product between del and f. You take the partial of p with respect to x, q with respect to y, and r with respect to z, and you add them up. Now let's look at Stokes' theorem, which is analogous to the curl form of Green's theorem. I won't go into details about the orientation of the boundaries and the surface. If you want clarification on that, I suggest that you go back to the textbook and read the descriptions there. I will just skip all that and just jump straight into the theorem. So we keep the left-hand side the same as Green's theorem, but on the right-hand side, instead of integrating curl f over a given region in R2, we're now integrating the component of curl f that is normal to the surface over the given surface in R3. So when you're having trouble remembering Stokes' theorem, just think of Green's theorem, but do it on the surface instead of on a plane. Now we look at divergence theorem, which is analogous to the flux version of Green's theorem. On the left-hand side, instead of integrating f dot n dr over a closed curve as a line integral, we're now talking about the flux in and out of a closed surface. So we're integrating f dot n ds over the given closed surface as a surface integral. We kind of do the same thing with the right-hand side. Instead of doing double integral over surface, we're now doing a triple integral over the volume enclosed by the given surface. To more intuitively understand this idea, let's suppose you have a balloon. You fill it up with water and you poke some holes on it. You let the water come out of the balloon. Water comes across the enclosed surface, which is the balloon in this situation. And the water's behavior when they travel across the surface of the balloon is totally determined by how the entire volume of water enclosed by the balloon behaves. Now, if you have taken college physics or AP Physics C, you might remember Gauss's law, which is essentially talking about the same thing. I will also recall Gauss's law when I'm having trouble remembering divergence theorem. Finally, in case any of y'all forgot how to do line integrals and surface integrals, no worries, I got you. For the line integral, you first need to have the curve parametrized by t. Then you can basically write dr as r prime t dt and go ahead from there. Pretty simple. Same idea applies to surface integral when you got a parametrized surface. I won't even try to prove this because it's kind of intuitive when you go ahead and do the calculations. But here's what you need to remember. Suppose you parameterize your surface with u and v. To calculate the surface integral, you basically replace ds with the norm of the cross product between the partial of r with respect to u and partial of r with respect to v times dA. Looks very similar, right? The norm term is in fact the distortion factor associated with this parameterization, if that makes it easier for you to remember. Now you might ask, what if the surface is explicitly defined? There is in fact a formula you can use in this case. The only difference is that for the distortion factor, you replace it with the square root of zx squared plus zy squared plus 1. Now this is all I have for today's video, and I hope you all have a great day.